Hey everyone, welcome to the first extra video for this course. The idea of these is basically they are concepts that you may or may not have seen before that are going to pop up in the class and things that I feel like having a video on them will be nice and helpful for you to learn about them or go back to if you forget something, things like that. So this first one's going to be about the complex numbers. If I can talk, that's helpful. Because we just hit the Euler equations for complex roots, and we're going to hit complex roots for the second order constant coefficient linear equations pretty soon. So a little bit of background on complex numbers will be helpful as to why we need them, why we care about them, why they show up, and how they're useful for solving these types of problems. So let's go ahead and start our little lecture on the complex numbers. So the main sort of building block or foundation for the complex numbers is what's usually denoted by math people as I. Electrical engineers might use J for this, but what I mean by I here is I mean the square root of -1. So if you've seen anything before, you know this is not a real number. There's no number whose square is -1. So what we do is we define this I to be the square root of -1. And what we do is we want to sort of build something out of this to make something we can actually use to do math stuff with. So what we talk about as the complex numbers are everything of the form a plus bi, where a and b are real. So 2 plus 3i. So square root of 2 plus pi I. These are all complex numbers. I just take a real number and add it to a real number times I. A in this case is called the real part, and B is the imaginary part. The real part doesn't have the I on it, the imaginary part does. So we want to be able to do things with these numbers, right? That if we can't do anything with them, there's no point. So we'll talk about a couple operations we can do here. The other ones also work, but they're a little longer to define. There's not really much of a point to go into them. So first thing is addition. If I have a plus bi, and I want to add c plus di, I basically just add them component-wise. So I get a plus c plus b plus d I. I add the real parts, I add the imaginary parts, and I get my combination that way. The other thing we can do easily is multiplication. I want to do a plus bi and multiply this by c plus di. And how this is going to work, it's going to work basically like foiling out. So I'm going to get an ac from the first term, and then from the last term I'm going to get bi times di. Right, but what is that? I squared is -1, so this is just minus b times d, and then plus ad plus bci. It just comes from foiling things out. You foil out the polynomials, and you remember that I squared is -1, so you can switch the I times I into a negative sign. I'll also note division also works, so long as the bottom is not 0. But it's a little more complicated to actually write out the formula, so I'm not going to do that. But just so you know that it does also work for division. Now, what's the point of the complex numbers, at least for this class? They have many, many uses outside of this class, but what's the point for this class? The complex numbers are super nice because they are what is called algebraically closed. Now, what this means is that any polynomial in the complex numbers, so with complex coefficients, factors completely over the complex numbers. So basically what this gives us back our fundamental theorem of algebra that you may have heard before. So I'm going to write it up there, and then we'll talk about why it's important and why it works for us. So here's the fundamental theorem of algebra. It basically says that any polynomial of degree n, so degree being the highest power that shows up, has exactly n complex roots, counting multiplicity. So what that means is something like x squared plus 1 factors over the complex numbers. It factors as x plus I, x minus I. If you work this out, you see that you actually do get x squared plus 1 when you factor this out. Also, say if you look at, say, x cubed minus 1, normally you would say this only has one root at positive 1. But over the complex numbers, it factors completely into x minus -1/2 plus root 3 over 2i, and x minus -1/2 minus root 3 over 2i. So finding those is not very easy, but it does factor entirely. It has 3 distinct roots over the complex numbers, And that is what's really nice for us because it means any quadratic we write factors completely over the complex numbers, meaning it has complex roots. If they're not real, it has two complex roots, and then we can use them to solve second order ODEs. It also works the same way for further ODEs, that when you get to third and fourth order ODEs, you know you're going to have 3 and 4 roots up to multiplicity. So you can use them to solve your equations. You know you're going to get the right number of roots to give you the right number of independent solutions to solve your equations. And this is why complex numbers show up, because we need these to factor our polynomials. Now the second way that we need to use complex numbers is using complex exponentials. So let's go into looking at that a little bit. So even though we're over the complex numbers, our properties of exponentials still hold. Namely, if I look at, for any two complex numbers, e to the x plus y, this is the same thing as e to the x times e to the y. And if I take a derivative of e to the rt, whether r is real, complex, or anything, I still get e to the rt times r. So these properties still hold even if things are complex. That's not too much of an issue. But now what I want to look at is what happens to the exponential of a complex number. So if I take r to be lambda plus I mu, so I have a complex number r, it is lambda plus I mu, then if I look at e to the r, what is that? That is just e to the lambda plus I mu. And using our first rule, I can split this up. E to the lambda, e to the I mu. This one we know about. This is fine. It's e to a purely real number. We can take that. That's just some value that we know. The question is, what is this? And the statement, which is known as Euler's formula, is the following. E to the I mu equals the cosine of mu plus I times the sine of mu. Now this may look really strange and kind of absurd, but that's how it works out. At the end of this video, I'm going to go through a proof of this using power series for those of you who want to see it. If you don't want to see it, you don't have to, but it's going to be there in case you want to look at it. So what's the summary here? I'll do a summary real quick, and then we will go into that proof. So summary, the complex numbers, which are also known as C with a line through them, so this is the complex numbers, is basically just A plus BI, where A and B are real. That's step 1, point 1. Point 2 is that every polynomial factors over C. And point 3, e to the I mu equals cosine of mu plus I sine of mu. Those are the 3 things you really need to know coming out of this video and know going into the rest of this class for the complex numbers. Now for those of you who are interested, I'm going to now go into the proof of this last fact using power series. If you don't want to, you can feel free to stop the video now and move on to something else. But for those of you who are interested, we're going to go into the proof of that. All right, so Euler's formula. I'm going to need power series. So what is the power series of e to the z? This is just the sum from k equals 0 up to infinity of z to the k over k factorial. All right, that is the power series for e. So now what I want to do is I want to plug in z equals I times mu. And now I'm going to split up the factors of stuff. So I'm going to have an I to the k times mu to the k over k factorial. Now, what do the powers of I look like? Well, I to the 1 is just I squared is minus 1, I to the third is minus and I to the fourth is 1, and then it cycles. So what I'm going to do is I'm going to split this sum into 2 parts, one that are even k's and one that are odd k's, because the odd k's are all going to have a factor of I hanging out on them, and the even k's are going to have no i's at all. So this is going to be the same as the sum over k even I to the k mu to the k over k factorial plus the sum of k odd I to the k mu to the k over k factorial. Now, what can I do with even and odd numbers? Well, I can rewrite them using the fact they're even and odd. So I can say let k here is going to be 2 times m, and k here is going to be 2n plus 1, because all odd numbers are the form 2n plus 1. So now I'm going to convert both of these series again. where this is all still e to the I mu, is going to be the sum from m equals 0 to infinity of I to the 2m mu to the 2m over 2m factorial plus sum from n equals 0 to infinity I to the 2n plus 1 mu to the 2n plus 1 over 2n plus 1 factorial. And now what I want to do is I to the 2m is just negative 1 to the m. And here I can pull an I to the front and then make this also negative 1 to the n. So let's do both of those steps and see what we see. So e to the I mu equals the sum from m equals 0 to infinity, negative 1 to the m, mu to the 2m over 2m factorial, plus I, sum from n equals 0 to infinity, negative 1 to the 2n, mu to the 2n plus 1 over 2n plus 1 factorial. And now if you go back to your calc book, you will see that this power series right here is exactly cosine of mu, and this right here is exactly sine of mu. With the I out front, gives me exactly Euler's formula. All right, cool, so it all works. That form is the thing that exists, and that gives us the way to turn complex exponentials into sines and cosines, which we're going to see is helpful later when we're talking about springs in motion, because we get oscillation. Where does the oscillation come from? It comes from the sines and cosines coming from complex exponentials. All right, thanks for watching, and the rest of videos will be talking about more specific stuff for the class, but this was a little bit of a detour into complex numbers to show you what you need to know. Thanks for watching, and I'll see you in the next one.